start section 7.3, which is about logarithmic functions and their graphs. We have 5 objectives. What is the definition of a logarithmic function? Graphing logarithmic functions. Evaluating elementary log functions, common and natural logarithms. Inputting logarithms, graphing logarithmic functions. Okay, so let's get started. A logarithm has a base of a, is defined to be the inverse of the exponential function with the base of a. And so that's important sometimes to remember that logarithms are inverses of exponential functions. And so the logarithms will follow exponent rules when we're working with them with equations. So if f of x is a to the x, then the inverse, f negative 1 of x, is log base a of x, is how you would read that. So in equation form, these two things are equivalent. X equals a to the y, and y equals log base a of x. And a is in both equations. Notice where a is, where y is, and where x is, because it's going to be important as we go back later and switch between logarithmic form and exponential form of an equation, because certain types of functions, you have to do one or the other to solve it. You have to be able to go back and forth from time to time. Alright, so it says use the definition of a logarithmic function to rewrite the following exponential functions as log equations. So we have 8 is equal to 2 cubed. 5 to the 4th equals 625. 7 to the x equals z. And so let's go on for that and look at their going from exponential, those are all exponential functions, to logarithmic functions. So we had 8 equals 2 cubed. It's going to be log base 2 of 8 equals 3. Okay, so let's go back and look at that. So when we look at these, okay, this is the base. That's going to be your base in the log function. This is going to be your answer in the log function. And this is what you're taking the log of. So it's going to be log base 2 of 8. And so in other words, this one will be log base 2 of 8 equals 3. Okay, so remember, looking at this one now, our base is 5, so it's going to be log base 5 of 625 equals 4. And right here, then, I like having it on the same page, so that's why I just stayed here to do this. Our base is 7, so I've got log base 7 of z equals x. The exponent part is always going to be the answer when you switch it to the log function. Now let's go back and put them the other way. So let's think about where we came up with this. The base is going to be 8 cubed is equal to 512. So this is 8 is the base, 3 is the exponent, and 512 is your answer. So we have 2 to the y equals x for this one. And somehow I missed the very first one, so let's go back and do that. That's going to be 3 squared equals 9. So we've taken those log functions and put them in exponential. And you're going to have to be able to do that. Okay. So these were the solutions, and you can read their explanations. It says sketch the following graphs of log functions. And so the graph, these all have vertical asymptotes. They're inverses of the exponential function. And so you remember the three the three points that were on the exponential function were 0, 1. Let me just kind of go back over that and remind you. This is the exponential function. Say I had 3 to the x power. Okay, and I wanted to graph it. Remember, one of the points, if I have x is 0, then y is 3 to the 0, which is 1. So one of my points is going to be 0, 1. Then if I have x to the first, then y is going to be 3 to the first, which is 3. So I have another point which is 0 or 1, 3. And then I have x equals negative 1. So that's y is equal to 1 over 3 to the first, or 1/3. So I have the point negative 1, 1/3. Alright, now remember, if we know that a logarithm is the inverse of the exponential function, then the points that should be on the graph, remember they're going to switch, so as they go to this graph, they become 1, 0, and then 3, 1, and 1/3, and negative 1. So in other words, it's 1, 0 is always on there. Then you've got base and 1, and you've got your 1 over base and negative 1. Are 3 points you can always locate on a logarithmic graph. Just the inverse, swap the points from your exponential graph. So if we look at the g, you can see we have 1, 0. We have 2, negative 1, because 1/2 to the negative 1 is 2. Remember, the half is a little bit of a problem. And we have 1/2, 1. Okay. Sketch the graphs of the following functions. Well, these are going to be a similar graph as 3 to the x, 2 to the x, 1/2 to the x, but they're going to be transformed. Grouped in with the x means it goes left or right. So in A, it's going to be left 2 and up 1. In B, if we factor out that negative, okay, let me go back. Okay, in B, you're going to have log base 2 of negative and then x plus 1. So I believe that one's going to be a reflection over the y-axis, but it's also going to be left 1. And h is going to be 1/2, so it's going to be facing a different direction from the other two that have bases of 2 and 3, and it's going to be down 2 because of the minus 2. The 2 is not grouped in with the x. And these are all the same transformations we did earlier. So let's look at them. Okay. The first one, we have shifted it. We see our base 3 graph in the green. Now we have the x plus 2 shifts it left 2 and then up 1. And so you can see that every point has gone left from our original graph, has moved over 2 spaces and up 1 space. Moved over 2 spaces and up 1 space, over 2 spaces and up 1 space. And there's our new graph. So you can graph that parent function and then move things over to see where your new function is going to be. And the asymptote shifted from x equals 0 to x equals negative 2, which it should. It should shift with the graph. Okay, looking at our next choice, we said it was going to be a reflection over y. You can see that it is. It also moved left 1, which we predicted. So the asymptote moves left 1. And so your points are all going to shift with it. Okay? It's left one and then it reflects over the y-axis. Alright, this one again was 1/2, so instead of opening down, it's gonna go up towards the asymptote and then curve outward, where the other one goes down towards the asymptote and curves upward. So this one is that because it's a half as a base, it's going to reflect over x, and then you have the upshift of 2, or it shifted upward 2 spaces. So it didn't change the overall shape, it just shifted the whole graph up. Or was it down? Let's look. Let me go back. It's down 2, I'm sorry, it's -2, so I was saying up. But this one shifts from the green as the original down 2 with each point. So each point is a downshift 2 because of that -2 in that equation. Okay. Evaluate the following log expressions. There's a couple ways you can do this. You can match the base. I can rewrite this 25 here as 5 squared. So I have log base 5 of 5 squared. And in that case, 2 is your answer. So you would say the answer was 2. Alright, another way to approach this, instead of matching the base, would be to say log base 5 of 25 equals x. Then change it to exponential form. 5 to the x equals 25, which is 5 squared. Remember from before, if our bases are equal, then our exponents must be equal, so x is equal to 2. Okay? It's probably a little easier when you have this fraction as a base to do it the second way. And so I'm going to say 1/2 to the x power equals 2. 1/2 is 2 to the -1 to the x, so that's 2 to the -1x equals 2 to the first. And so x is going to be equal to -1. So our answer for this one is going to be -1. And then log base pi. This one actually would be easier probably the first way. So we have log with a base of pi. Square root of pi is pi to the 1/2 power. If we remember rational exponents. If our bases match, this is our answer, the exponent. And so our answer for this one would be 1/2. Alright, so let's just go and check a couple of them. Make sure we're right. I have to get out of my annotation mode. Alright, so log base 5 of 25, it's 2. Log base 2 of 1/2. Again, they rewrote it with matching powers. I think it's kind of easier to do it the other way. But again, they still got -1. And then log base pi of pi will be 1/2. So we got the first 3 right. Let's go back and look at the next ones. We've got 17 to the log base 17 of 1. I'm going to go ahead and put equals x here. Okay, 17 to the x equals 1. Well, you think, how can I get 1? Well, the way you get 1 with an exponent is if you remember anything to the 0 power. So I can make 17 to the 0 power, but anything to the 0 power is 1. And so my answer will be 0. If your answer is, if you're trying to take the log of 1, your answer is going to be 0. Because anything to the 0 power, if you remember a logarithm is an exponent, then anything to the 0 power will give you that 1. Log of 16, again, I'm going to sort of employ this where I say 16 to the x equals 4 to the first. 16 is the same as 4 squared to the x power, which means that's the same as 4 to the 2x equals 4 to the first. So now we have 2x equals 1, and so x is equal to 1/2. Okay. Log base 10, 1 over 100. Well, 100 is 10 squared, but it's in the denominator. So if we want to match bases here, you could do it that way. Log base 10 of 10 to the negative 2. That's 1 over 100, 10 to the negative 2. So our answer is going to be negative 2. Okay, so let's look back and double check. Make sure that, again, they agree with us. We are going to go through, we've already done these. Here's log base 17 of 1. Again, it's 0. 16 to the 1/2 power is 4. And so it's 1/2. And f is negative 2. And I showed you a couple ways to do that maybe helped a little bit different than what they have in the notes here. Okay, solve the following log equations involving logarithms. All right, well, let's look at this. We have 6 to the negative 1 is equal to 2x. Is one way you can rewrite that. We can rewrite this as exponent. If you see the word log only on one side, many times it's best to just put it in exponential. So we have 6 to the negative 1 is equal to 2x. 6 to the negative 1 is 1/6. So then if I multiply by 1/2 or divide by 2, either way, x is going to be 1/12. Okay? And then let's go over to this last one. Do the same thing. We're going to put it in exponential. 2 to the 5th is equal to 8 to the x power. Well, I can make 8 with a base of 2. 2 to the 5th is equal to 2 cubed. 8 is 2 cubed to the x power. So 2 to the 5th is equal to 2 to the 3 times x. So 5 must be equal to 3x. And so 5/3 is equal to x. Okay. Now, I don't know a great way to explain b and work it out. If we took the log of both sides, you would have log base 3x of 2 times log base 3x of 3 equals log base 3x of 2. And I don't think that's going to give me an easy way to explain. The answer is, let's just go through their explanation on this one and see what they have to say. Somehow I'm not getting my eraser to go on here. So let's go back. And solutions here, we convert it to exponential, and we have 1/12. For this next one, we convert it from exponential form to log form. So log base 3x of 2 equals to the log base 3 of 2. Okay, here's what they did. I can explain that. Alright, so they took the log base 3 of both sides. So one of the rules is you bring that log in front. So I have the exponent that comes in front is the log base 3x of 2. And then we have the log base 3 of 3. And the log base 3 of 2. So we took the log base 3 of both sides. Well, here our bases match, and that's 3 to the first, so all of this equals to 1. Okay? So that's how we came out with what we have here on the left. We have log base 3x of 2 equals to the log base 3 of 2. That's why it's the log base 3. Because we took the log base 3 of both sides. Okay? So now let's look at the next step. Okay? So if the log base 3x of 2 and the log base 3 of 2, we're taking the log of 2 and they're equal to each other, 3x must equal 3. So we're equating the bases just like we did in exponential equations. So x is equal to 1. And then we did this one and got 5/3. Okay. Now, log base 10 is called a common logarithm. You don't write the 10, it's just log of x. And that's one you can do on any calculator. Log base e is a natural log. It's called ln. It's understood that the base for ln is e. Both of those are things you can do on every calculator. Some calculators will do other bases, but many of them will only do base 10 and e. So evaluate the following log expressions. So let's look at these. Okay. Natural log means that our base is e. I'm going to go ahead and write it in there. And e, cube root of e is e to the 1/3 power. So again, we've made our bases match. Our answer is going to be 1/3. Okay. Natural log of 4.78, you're going to have to put this in a calculator. Any scientific calculator will get that. Just punch the ln button and 4.78. That's going to be the same with D, only you'll push the log button. Okay. Now the log base of 1,000, we know that's base 10. It's not written, but since there's no base there and it's log, we know that's the same as log base 10. And 1,000 is 10 to the 3rd power. Bases match, so 3 is my answer. Okay, so let's go through. Solutions. No calculator necessary. The answer is 1/3. B, same thing. C, put it in the calculator. And you're going to get 1.564. And D, same thing, put it in the calculator and get 1.021. Okay, graphing log functions. Weren't any graphing log functions other than let's go back here to what it says. Let's look through that since they didn't have examples. Okay. You can put them in the calculator, hit y equals. Graph appears to cut off around the point where x equals 3. So we know it doesn't really stop. It just approaches that asymptote and then keeps going straight down. So you may have some things where it looks funny on the calculator. I think this is what it's trying to say. But you can input log functions on the calculator, just y equals log. You can't put a base in. It's going to have to be log base 10 or natural log to put it in the calculator. Okay. So that is the end of this 7-3.